I have the pleasure to chair that session, and we'll start right away as the bell has rang already with the first talk that will be done by Mr. Sime Malenica from Bureau Veritas in Paris.
Yeah.
Up to you.
Thank you. Hello to everybody. Sorry to not be there. I was initially planning to come, but it was not possible finally. So I will talk about the interaction of flexural gravity waves with the vertical cylinder up to second order. So this problem has been solved many times for linear problem, but for second order I was not able to find the solution in the literature. So we decided to revisit first the linear case and to make it in a way to be extendable to second order, and then we propose the solution for the second. So this is the content of the presentation. So first I will say a few words about the basic principle of linearization, which is useful to recall even if it is not nothing, there is nothing new in it. Then I will talk about the solution of the linear problem, which, as I said, has been solved already by several type of methods. And then I will present the solution which we propose for the second order solution. And then I will consider some special cases and conclude with few words. So this is the context of the problem. So floating body, in the present case, it is fixed, but it applies to the theory applies to floating body too in ice, and ice is linked to the body in a certain way. So the first things to do is to actually, sorry, as I said, the problem has been considered by many authors, and this is the incomplete list of the papers. I put only those which I used, actually, which we used as inspiration, say. And before going to the way in which we will solve we are solving this problem, just to introduce the basic principle of the boundary value problem, which has to be solved. So the situation is very similar actually to water waves, except that the free surface slightly changed. We need to introduce the law, physical law, in which the plate or ice deforms. So kinematic condition remains the same, meaning that we say that the surface of the interface is material surface, and it remains material for all time. And the dynamic condition describes how the free surface deforms under the action of the external loads, which is the pressure. So gravity and pressure, which comes from Bernoulli equation. So these are two classical conditions for water waves, for any type of waves. We can combine two conditions in one, and then we have something a little bit more complicated, but still very similar to water waves. The capital H is the operator which is linked to the plate deformations, and when we have water waves, this capital H is equal to 1, and all the terms keep. I mean, the formulation is the same just by putting capital H equal to 1. So the nonlinear problem needs to be linearized if we want to solve it in a say simpler way. We can look for solving for fully nonlinear, but it's not the purpose of this work, and it's much more complicated. So linearization means that we introduce the perturbation series in the solution, like usually for any quantity, and then we use the Taylor series expansion in order to define the problem on the fixed boundaries. So the domain, physical domain, when we linearize the problem is fixed. By doing this and putting this perturbation and using Taylor series expansion, we came up with this linear free surface condition and this second order free surface condition. So this is first linear free surface condition is something well known. Say it's homogeneous. There is no forcing on the free surface. The second order solution keeps the similar form, but it is non-homogeneous. So there is a forcing term on the right-hand side, which comes from the first order solution. So this is something classical in wave free surface wave problems. Then the next step is it is useful and common to work to consider time harmonic flow and to describe the problem in frequency domain. So again, classical. If you have a only monochromatic wave, then we have this expression for the linear potential. So real part of the complex potential phi and time harmonic term. At second order, it follows by linearization that we will have one constant term and one term which evolves on the double frequency. So our concern is this term on double frequency. So once you introduce these expressions for the velocity potential into the time domain free surface conditions, you end up with something like this. So linear case, you have this wave number, and you have non-homogeneous free surface conditions. At second order, you have something similar, and you have a non-homogeneous term on the right-hand side. So this operator kappa 1 comes from the describes, say, the behavior of the plate, mechanical behavior of the plates. At second order, it's similar, but the wave number becomes 4 times the one from linear curve. So once again, for water waves, we have this capital H, which makes that the kappa 1 and kappa 2 are equal to 1. So by putting 1, we recover water wave problem. So all the idea here was to generalize the water wave problem and then use the same method that we use for second order solution in water wave. So this is the once you do that for the case of the fixed vertical circular cylinder, you end up with this generic boundary problem. Generic means it applies for a linear and second order case. So you have normal velocity at the cylinder equal to velocity of the cylinder, which is not 0 at second order, neither at first order for the perturbation potential. Needs to cancel the velocity induced by the excitation, which is the incident wave. So at the free surface, we have, as I said, similar condition at first and second order, except that at first order we have homogeneous, Q is equal to 0, and at second order it is non-zero. And at the bottom we have normal velocity equal to 0, and we have Laplace equation in the fluid. So this is if we know how to solve this problem, then we can consider linear second order or even higher order problem in the same way. So in order to make the things a bit more clear, we separate the total potential into what we call body perturbation potential, which means we have homogeneous free surface conditions and non-homogeneous body boundary conditions. And for free surface perturbation potential, we have the opposite, means non-homogeneous free surface condition and homogeneous body condition. So this is just to make the things a bit more clear and kind of systematic. So we can define, similar to waterways, we can define the dispersion relations for the flexural gravity waves, which is a bit different from the waterways, but it keeps the same form. The eigenfunction expansion, which is used in this work, is also something similar to waterways. We consider flow to be symmetric about x-axis, so we have the Fourier series only in cosinus mode. In vertical direction, we develop with the vertical eigenfunctions, which where these eigennumbers follows from the dispersion relations. And in contrast to the waterways, we have, in which case we do not have complex roots of the dispersion relations. Here we have one real root, infinite number of imaginary roots, and 4 complex roots. So this is the difference with waterways. In waterways problem, we do not have these 4 complex roots, but that's okay. We just have 4 more, and we continue using the same methods. Orthogonality relations, which we need to use when we use this eigenfunctions expansion method, are also a bit different than for the waterways. There is in particular this term here, which occurs, which is 0 for waterways. But okay, that's a different orthogonality relation, but okay, we keep using them. We also can define the green function of the problem, similar to waterways again, except that in vertical direction we have more eigenfunction than in a waterway case. But the expressions keeps to be similar. So now I explain how do we solve body perturbation potential, which is in fact equivalent to the linear solution. So classically we develop the solution into eigenfunction expansion form. We use the body boundary condition, which is which states that the normal velocity of the fluid is equal to normal velocity of the body, or total velocity is equal to 0, where Vm is the external imposed velocity. You use the orthogonality of the eigenfunction, vertical eigenfunction, and you end up with this expression, in which you have this forcing from the body, because body boundary condition is not non-homogeneous. And we compared to the waterways, you have this additional term, which accounts for the fact that there is a plate on the free surface. And then, since you will have more unknowns, then you have these eigen expansion equations. You need to account for the edge condition. You need to say what is happening at the end of the plate. So which came out in these 2 terms here, which need to be found, which are unknowns and need to be found in the solution to complete the solution. So to simplify the notation, it is common to describe them just by gamma m and sigma m, and whatever the boundary conditions, the edge conditions, the 2 equations for these unknown coefficients can be written in this form. So this is something which was given in one of the papers, I think by Bhattacharya, which I found really very elegant. So whatever the edge condition, you can write like this. G1 to G6 will change, but that's the basic principle. So it is also common to solve the problem using the not eigenfunction expansion method, but at the end it comes to the same because the green function is expressed in eigenfunction form. But anyway, you can use Nonlinear equation method to arrive to the same result. It's a little bit more complex to show how this free surface integral, which occur when you close your boundary, when you take into account all your boundaries, how it change. So you need to use some integral transformation to write it in the form that involves only the boundary of the water line. Then, if you write this boundary equation for the point inside the cylinder, where you know that green theory gives you 0, you can use the orthogonality and just proceed in similar way as in eigenfunction expression method, and you end up with this expression, which is actually the same as the one which I presented before. The reason why I'm talking about boundary equation is that it is easily extendable to the second order, or what we denoted as free surface perturbation potential, in which we have at the free surface we have this non-homogeneous term Q. So the integral at the free surface in the second order problem will not disappear. We will have this expression. So this is the for body perturbation potential, the forcing of the solution is at the body, and here it is at the free surface. So when you apply the orthogonality relation, use some integral identities at the free surface, you end up with something like this, which is very similar to body perturbation potential, except that this term here now concerns the forcing at the free surface and not at the body, as it was the case for the body perturbation potential. Maybe I can come back to show. So you see, this is the expression for body perturbation potential with the forcing at the body, and at the for the free surface perturbation potential, situation is similar concept, say, but the forcing is at the free surface. Same as for the body perturbation potential, we need to close the problem by 2 additional edge conditions, which came out in similar way. So now, so that's the procedure to solve both linear and second order. So as I said, we have been inspired solving this by what we did in the past for water waves, in which these terms, all the terms associated with D in these edge conditions disappear, and we have only this part of the solution, which is something classical for second order water wave. So to show that the solution reduced to the classical solution in the water waves, we consider that there is no plate, so the special relation becomes like this. Orthogonality relations are simpler, and body perturbation potential is given by a simpler expression, and same for free surface perturbation potential, it is given by simpler expression. So that means that the solution that we propose generalize in a quite, I would say, elegant way the solution of the water wave. As a special case, we consider the wave diffraction, because this body perturbation and flexural perturbation can be applied both to the diffraction and radiation, means for fixed and moving body, but when applied to the wave diffraction, water wave diffraction, we can show actually not water wave, but pure wave diffraction, which means the interaction of the flexural gravity waves with the fixed cylinder, we end up with this solution. So this solution, just by putting the relevant expression for the incident wave and using the expression that I showed before, we end up with this expression, which is equivalent, identical, say, to the one given in the work by Korobkin and Tanya in one of those their previous papers. So that means that we are fully equivalent. And if you consider water waves, you end up with Makami and Fuchs solution, which was expected. So that was the theory of which we developed. The numerical implementation, unfortunately, was not done yet, because there was no personally, I didn't have time. We didn't found someone to work, because the problem is quite complex. It requires maybe a PhD student or something. So in conclusion, I would like to say that we developed an alternative method, which is for linear case produce the same result as the other methods which were proposed. Due to the rather elegant, say, way to build up the solution, the extension to the second order problem was done in a similar way as for the water wave problems. So the further work we can imagine is to implement already the second order solution. There is something I was not talking about in the presentation, which is the plate equation was kept linear, which in practice is not necessarily the case. We are not really strictly speaking allowed to keep it linear, but we can introduce we should introduce nonlinear terms if we think they are important. We can also think about general numerical solution based on the green function to be able to solve for any geometry of the plate ice. And if we would like to produce the semi-analytical type of solution, all these cases, which means plate and circular plate or multiple circular plate, can be easily, let's say, considered using the eigenfunction expansion method in the same way as this is done in water wave problems, which is something rather straightforward. So this can produce reference results for numerical check, or even if the configurations are in physics like they are, can produce already useful solutions. So that's the end of my presentation. So thanks for your attention. And if you have any question, please. Hello. Hello. I cannot hear you.
I would like to.
Hello. Hello?
Hello? Yeah,
Hello?
sorry. Yeah. Do you hear us?
Yes, I hope you were able to hear me.
Yeah, we had some problems over here. Sorry for that. So we are now taking questions from the audience. Thank you for your presentation.
Did you hear the presentation or?
Very well, very well.
Okay,
Yes,
good.
that was very clear. It's just that we lost the mic here, contact with you in outer
Okay.
space. Houston is back. So are
Okay,
there
if
any
you can-
questions? Yes, one here, one question coming.
Thank you, Sime, for presentation. This is Korobkin. Looking at, following your presentations, came to my mind that you did elastic column in the past in waves. So it seems that you can do, or you can combine these problems and to analyze the elastic vertical column and ice clump to it as well. It would be interesting problem, I believe. Would you comment, please?
I agree with you. This decomposition, which we did actually together in body perturbation and free surface perturbation, is very general. So what will change for the elastic cylinder is just we will have, for linear case, say, we will have just this body perturbation potential, which will take into account natural modes of the column in the same way as we did for you see. Can you see my screen or not?
Yes.
Yeah, okay. So this expression here, not this one, for linear case, here, this Vm, which is the Fourier decomposition of the velocity, whatever the velocity is. In this case, it is velocity of incident wave, but in the case of deformable column, it will be the velocity of deformation of the column. So the solution remains exactly the same, and that's why I like this approach, and both for first order and for second order. So everything is possible. I mean, the problem is this problem is generic. Whatever the condition on the body, whatever, is it moving or not? Once you linearized your domain, your fluid domain is fixed, and then you just apply the conditions of this type wherever, and you change whatever you want in the condition. So that's, I agree with you. It can be an interesting problem.
I think there's a follow-up question. Yeah.
Thank you, Sime. I noticed that you did not perturb the condition at the contact line where ice is clamped to the cylinder. So because this is in for rigid cylinder, this line is this line doesn't move, so
Yes.
there's no perturbation. But if the cylinder is elastic, this condition would give also forcing term, I believe. So it's turned it come to my mind that the problem is the more complicated and actually quite a rich problem with ice. And also you mentioned that just that integral change. I think it's the more substantial change, because the problem is coupled. So you need to find deflection of the ice and deflection of the column. So it's coupled.
You are right. You are right. It might be more complicated, but in any case, the edge condition at the plate will keep the same form, but it will be a bit different. But we will keep the same form. I guess actually, I hope so, that we will be able to end up with this with this type of additional equation for which account for the edge condition. But we need to see more in details. Right.
Excellent. Thank you. Are there any more questions? Otherwise, we'll just thank you again and move on to our next speaker. Thank you.
Thank you very much. Thank you.
So our next speaker is Tatiana Khabakhpasheva, who's going to present on hydroelastic waves propagating in the gneiss channel. On to you.
Okay. This is my name, Tatiana Khabakhpasheva, and just pronunciation, because in many cases it is like